Hello everyone, welcome to Helm of Science. Now we are meeting after a very long time. I hope all of you are doing well and are safe during the present situation. Today we are going to start with one of the most trending topics and the most interesting topic of class 12, that is coordination chemistry. So let us begin with coordination chemistry. So basically, before we start the topic, let me just tell you that this topic forms a major portion of our class 12 board syllabus in terms of the organic part, right? I mean the inorganic part. So in respect to the inorganic portion that is included in your class 12 syllabus, coordination chemistry plays a very vital role. Clear? So let us begin coordination chemistry. Now, before we understand the term which is coordination, we need to understand where has this term come from or what is the starting point or foundation of this term. Now, coordination basically comes from the term coordinate bond. I repeat, coordination basically comes from the term coordinate bond, right? Okay. Now, to understand coordinate bond, first things first, we need to recapitulate a few of our previous knowledge that we have of the previous classes. If we go back to our previous classes, you will know or you'll recapitulate the terms bonding which we have done in class 10 and 11. Now, in bonding chapter, we have learnt about three types of bonds. So, before I begin, let us broadly classify what we are going to discuss right now. So, we are going to discuss about bonding, which we had classified into three parts. One was ionic bond or electrovalent bond to be precise. Another was covalent bond. And there was a third category which few of you might have been introduced to and some of you it might be completely new. So we'll consider it later. Okay. This part we'll talk about later. But firstly, these two portions, that is ionic and covalent bond, is something which we all have studied in our junior classes. Now let's get a quick revision of it. That is, ionic bonding was actually referred to as bond formed between two ions, right? Bond formed between two ions, or if I would be a little more precise, it was referred to as bond formed between a metal and a non-metal. Metal and non-metal. This was what we had classified ionic bond as. Now, if I would use the chemistry terms, then I would say ionic bond was referred to be a bond formed between two entities having a striking electronegativity difference. Ionic bond was referred to as a bond formed between two entities having a striking electronegativity difference. Right? Now, what do I mean by electronegativity difference? In very simple or any lucid language, I would say that it is a metal and a non-metal. Now, if we try to revise how the bond was formed, basically, you would see that the bond was formed keeping in mind the octet rule that we had learnt in our junior classes. Octet rule, right? So, what was the octet rule? The octet rule was the rule which stated that any entity, any atom should have at least 8 valence electrons in its outermost shell, which we refer to as the valence shell, right? So that was the octet rule, and the ionic bond was formed keeping the octet rule as a foundation, as a basis, right? Now, let us take a small example to ionic bonding and understand what it was actually, right? So, if I have to take the example of, suppose, magnesium oxide, MgO. Now, magnesium oxide is made up of two entities, one metal, that is magnesium, and the other is a non-metal, that is oxygen. Now, if we have to understand, firstly we need to understand that this compound would undergo an electrovalent bond. Why is it so? Because we are seeing that there are two components which it is made up of. One is magnesium and the other is oxygen, which have a striking electronegativity difference. Or if we have to say it in very simple language, then one is a metal and the other is a non-metal, right? Now, let us write the electronic configuration of both of them, starting with magnesium. So, the electronic configuration for magnesium would be 2, 8, 2. Why is it so? Because magnesium has an atomic number of 12, right? Whereas, similarly, the electronic configuration for oxygen would be 2, 6. How do I know? Because the atomic number is 8, right? So, the first shell would have 2 electrons and the second shell would have 6 electrons. Now, owing to the octet rule satisfaction, we would see that this entity, that is magnesium, needs to lose these 2 electrons in its valence shell so as to attain their nearest noble gas configuration or to attain the stable octet configuration, right? So, in order to do so, it has to lose these 2 electrons which is present in its outermost shell or its valence shell. Similarly, if we come to oxygen, in order to maintain or satisfy the octet rule, it needs 2 electrons in its outermost shell. So, how is that possible? Only if somehow these 2 electrons come to oxygen, right? Then only what will happen, by the increase of 2 electrons, oxygen would attain its stable octet configuration, whereas magnesium would gain its octet configuration by losing its 2 electrons. Now, one thing, it's very basic, but the concept needs to be clear. That is, whenever there is a loss or gain of electron, electrons cannot fly in the air or in the atmosphere just like that. If somebody is losing electrons, there has to be a counterpart which will accept those 2 electrons. It cannot happen this way, that somebody loses an electron and it just vanishes in thin air. That is not possible. Why? Because we have already studied about the law of conservation of mass in our junior classes, which gets violated if such a situation happens that electrons are vanishing into thin air, right? So, if magnesium has to lose its 2 electrons, then oxygen has to gain those 2 electrons to maintain that balance, right? Okay. So, how do we depict the bonding on pen and paper? That is, magnesium being, firstly, if you have forgotten, just let me remind you that we only draw the valence shell electrons and not all of the electrons, just for the sake of simplicity, right? Okay. So, before starting to draw all of these shells one by one, just keep in mind we do not do it according to Lewis dot structure. We maintain the simplicity and only refer to the valence electrons. So, magnesium has 2 valence electrons, right? So, this is the 2 valence electrons, okay? And oxygen has 6 valence electrons. So, I am just changing the symbol of the electrons to omit any kind of confusion that might arise in your mind. So, there are 6 valence electrons, right? Okay, so what happens? Magnesium transfers its 2 electrons to oxygen, like that. Alright. Once magnesium transfers its 2 electrons, what happens is magnesium gains a charge. Now, what charge would it be? It would be a positive charge. How do I say so? Because whenever our entity or an atom loses electrons, it gets a deficit of electrons, right? There is a shortage of electrons. And in order to refer to the shortage, how would we say? We would refer to it as a cation or as a positively charged species. Now, since it has lost 2 electrons, we would refer to as Mg plus 2, right? Similarly, on the other hand, oxygen has gained 2 electrons, so it has an excess of electrons, which we refer to as an anion or a negatively charged species, shown as oxygen 2 minus. And when these two ions come and form a bond, they generate the compound magnesium oxide, which shows the formation of an ionic bond. Why ionic bond? Ionic bond because we have actually come across the formation of ions here. So that's our general discussion regarding ionic or electrovalent bond. Now we come to the second classification or the second subcategory to bonding, that is covalent bonding, right? So we'll talk about covalent bonding now. Now, ionic bonding actually showed the transfer of electrons, or if I may say so, it actually showed the gain or loss of electrons in a particular compound, right? Covalent bonding actually refers to as sharing of electrons, alright? So, it is nothing but sharing of electrons. Sharing of electrons, okay? Now, how would I show sharing of electrons, or what do I mean by sharing of electrons? First things first, sharing of electrons is also based on the rule which we have already referred to in electrovalent bond or ionic bond, that is the octet rule satisfaction. But here we would also consider the duplet rule. Now, you might ask me that why have I not referred to the duplet rule in ionic bond and why suddenly duplet rule in covalent bond? Okay. Firstly, see, duplet rule actually means possession of 2 electrons in its valence shell. I repeat, duplet rule means having 2 electrons in its valence shell, right? So, if the nearest entity which might have 2 electrons in its valence shell is the group which is group 1. Now, why do I say so? See, not exactly the entire group 1. If you follow the group 1 elements, hydrogen and lithium would be the ones which would show duplet rule rather than any other element. How is it so? See, if we go further down, that is sodium, potassium, etc., you would see in order to attain a stable noble gas configuration, it will have to fulfill an octet rule. Why? Because for sodium, the atomic number is 11, so 281, right? So, in order to attain a stable configuration, it has to fulfill the octet rule instead of the duplet rule, because the penultimate shell, that is the one which is before the valence shell, has 8 electrons. So, in order to attain the octet rule, it has to lose the 1 electron in its valence shell in order to make itself stable, right? Similarly, for potassium, it is 2881, right? For potassium, it is 2, 8, 8, 1, right? So, for it also, it can satisfy the octet rule rather than the duplet rule. But if we come back to the ones here, that is hydrogen and lithium, atomic number for hydrogen is 1 and for lithium it is 3, right? So, for lithium, if we write the electronic configuration, it would be 2, 1, right? So, in order to attain a stable configuration, it has to follow duplet rule instead of octet rule, because it does not have a scope of attaining the octet configuration in this case. So, it will attain the duplet rule, which I did not mention in the electrovalent bond section. But to be very clear about it, since the number of species that would attain the duplet rule is limited, for example, lithium, then you have beryllium, boron, since it is restricted to these three elements, that's why I have not mentioned it in the electrovalent bond section, but that doesn't mean it is not going to happen. It will happen the same way as we talked about the octet rule satisfaction, right? So that is going to happen in case of lithium, beryllium and boron also, but just instead of octet rule, it will be duplet rule, right? Okay. Now coming back to hydrogen. Hydrogen is one such entity which can behave as a metal, or if I may say so, not a metal exactly, but a positively charged species as well as a negatively charged species, hydrogen, right? Now, if hydrogen has to form a positive charge, then in that case, it has to lose its one electron that is present in its valence shell, right? Now, if it has to lose the one electron, then there will be a situation where the shells which are present in an atom will have no electrons, whereas the nucleus that is present in the center would have one proton, right? Now, such a situation is in technical terms not required. Why do I say not required? Because it again violates the basic rules of stability. Why? Because an atom is electrically neutral, right? An atom is electrically neutral. Now, if and only if it has to form the plus one species, right? If and only if it has to follow the plus one species, then it has to lose its valence electron so as to behave as a metal or a positively charged entity. For that, it has to lose all its electrons from the valence shell and only have one proton in the nucleus. So we are actually saying that an atom is only having positive charge, whereas there are no electrons present in it. Now, logically speaking, that is not possible because we have already learned it in our junior classes that atom is electrically neutral. So, such a situation to happen is a bizarre situation, right? That is why if you have noticed in your junior classes, whenever we refer to as acids, the term acid, we have already always said that acids are species that donate H3O plus ions and not H plus ions, right? Why have we said so? Because H plus ions is this situation which I have just outlined right now. That situation does not exist. So in that case, we cannot say acids are species that donate H plus ions. Acids are actually species that donate H3O plus ion. Now, how is this H3O plus ion? Is an example of coordinate bonding, which actually makes H plus 1, which is not possible to find, stable through a bonding which is known as coordinate bonding, right? We'll refer to it in the later part of the class, but first things first, where we were in this covalent bonding section. Now, what was I explaining? I was explaining that sharing of electrons is the fundamental criteria for covalent bonding, which also follows the same characteristics or the same rules as that of ionic bonding, that is the octet and the duplet rule. Now, let's just quickly get into the details of covalent bonding a little bit. Suppose we have to form the compound HCl, right? So, we need to form this compound HCl. Now, there will be two categories of students who will approach this question. One, that ma'am, H and Cl are the two atoms that are forming this compound. both H and Cl have a striking electronegativity difference. So we might as well say that HCl will form an electrovalent bond because H will behave as a metal here and Cl behaves as a non-metal here. So we can conclude that this compound forms an ionic bond. To which I would say that it's absolutely wrong. Why? Just let us discuss the electronic configuration, then you'll realize why I say that it's wrong. The electronic configuration for hydrogen is 1. Why? Because its atomic number is 1. And the electronic configuration for chlorine is 2, 8 and 7. 17 is its atomic number. Now, if we come to chlorine, then it needs 1 electron in its outermost shell, right, to satisfy its octet rule. So far, it's matching the criteria of ionic bond. If we come to hydrogen, in order to follow any of the rules, both octet or duplet, it cannot give its 1 electron. Why? Because forget about octet rule, even if it gives its 1 electron, there is no chance that it will follow any 8 electronic configuration in its valence shell. Coming to duplet rule, that is also not possible if it loses its 1 electron. But it is possible to follow the duplet rule if it gains 1 electron, right? If somehow it gains 1 electron, right? Now, there is no such species in its vicinity apart from chlorine which can give 1 electron to it so that it can gain the electron and form the duplet rule. Why? Because if chlorine gives 1 electron, then it would become 6 electrons in its valence shell, again violating the octet rule, right? So, in no ways can HCl form an ionic bond because of lack of contribution from its surrounding atoms, as well as it itself cannot do anything in order to satisfy octet or duplet rule, right? So, the question that had come in our minds that HCl might undergo an electrovalent bond is not true, right? So, how would we justify the bonding of HCl? HCl here will undergo covalent bond. Now, in the beginning of the introduction to covalent bond, I had stated that covalent bond means sharing of electrons. Now, let us just draw the two atoms. Now, H has 1 electron in its outermost shell. So, let's just draw that. And Cl has 7 electrons in its outermost shell. So, 1, 2, 3, 4, 5, 6 and 7. Right? Now, Cl needs 1 electron in order to complete its octet. And H needs 1 electron to complete its duplet rule. So, what happens in this case is H and Cl share their electrons. Now, what happens? See, when H shares its electron with Cl, then H has a total of 2 electrons. See, 1 and this electron that it has shared from chlorine. Whereas chlorine fulfills its octet by sharing its electron with hydrogen. We'll just check it right now. 1, 2, 3, 4, 5, 6, 7, which was its own, and the one which it has just shared, right? So, both have attained their respective octet and duplet configurations by sharing their electron. Now, what happens? Sharing of 2 electrons results in the formation of a single bond. So, H and Cl form a single bond among themselves, resulting in the formation of HCl, which is a covalent compound, not an electronic or electrovalent compound. Clear? Okay. Now, these were the two broad classifications which we have studied in our junior classes up till now. The third classification, which I mentioned in the earlier part of today's class, was coordinate bonding, which we shall discuss right now. So we shall start with coordinate bonding, which is the most important part of this chapter, actually, because it justifies the topic of the chapter, right? Okay. So coordinate bond is actually a bond which becomes, how do I explain? Coordinate bond is something which we would refer to as, see, there is a thing which we say that it's actually a negotiation. How do I put the word negotiation? See, suppose you and your friend have gone to a park to play, right? Okay. Now there is just one swing available for both of you to ride on, right? So what you can do, there are two options. One is that one of you just keep swinging and do not let your other partner have a ride. This is one scenario. And the other scenario would be you kind of make a bond between each other, or a kind of negotiation that for 15 minutes, one of your friends shall ride on it, and for the next 15 minutes, the other one will have a chance to ride the swing. Now, these are the two cases which is available, right? The second case, where there is a kind of mutual understanding or a mutual negotiation that either of you will ride the swing by turn or turn by turn, is actually a basic part of coordinate bond. Now, in coordinate bond, none of the atoms, or the mother atom that is, does not want to lose its electrons completely. Now, why mother atom? We need to take an example for this. Now, just a couple of minutes back, I had referred to this compound, H3O+, and I had said that acids are defined as compounds which form hydronium ions as the only positive charged ions, and hydronium ion is actually H3O+. Okay. Now, how would we describe this compound? Okay. H3O+ is actually made up of two parts, H2O and H+. Okay. Now, this part, H+, is something which we just saw. Very difficult to explain. How would it be formed, right? So, let's not think about it right now. Let's concentrate on this part first. That is water. Water is made up of two entities. One is hydrogen and one is oxygen, right? So, the electronic configuration, I am just using the terms EL accordingly for each of the entities. For hydrogen, the electronic configuration is 1, and for oxygen, the electronic configuration would be 2,6. Correct? Okay. Now, the same situation that we saw just a few minutes back, that hydrogen, in order to complete its duplet configuration, it needs to share its electrons, whereas oxygen needs to share its electron with hydrogen in order to attain the stable octet configuration, right? So, since there are two hydrogen, we'll just write it that way, two hydrogen on both sides. Now, you can write it as your wish, right? You can depict the diagram as per your choice. There is no such rule to it. I have written it just for the sake of the simplicity of the diagram, right? Okay. Now, hydrogen has one electron in its outermost shell, and oxygen has 6, right? Now, oxygen shares one of its electron with this hydrogen and the other of its electron with this hydrogen. So, effectively, it actually forms two single bonds with hydrogen, like that. And it is left with two pairs of electrons. Two electrons constitute one pair. So, it is left with two pair of electrons, right? Which we refer to as lone pairs. Lone pairs. I am sure you're aware of this term, but since we are going through a revision part, so let's just discuss everything in detail, right? So the pair of electrons which are left behind, which do not participate in bonding, are referred to as lone pairs. Okay. Now, H3O plus is made up of H2O, which we saw right now. And there is one more part to it, which is H plus. Now, what does or where does H plus come into the picture? Now, H plus is something which is not stable, which we just said. So, what happens is H plus comes into the picture like that. And it asks for help from water or from oxygen to be precise. Why? Because oxygen has excess electrons here. So, it asks help from it. Now, oxygen is very adamant and very moody, right? So, oxygen says that I am not going to give you both of my electrons. It's not willing to give its electrons to this H plus ion. Why? Because, as I said, it's very adamant, very jealous, and very moody. So, it says, okay, we'll just make a contract between ourselves that I shall give you the 2 electrons which you need in order to keep yourself stable. Why? Because it needs minimum of 2 electrons to complete the duplet rule. So oxygen says that I'll give 2 of my electrons to you so that you can complete or fulfill your duplet and stay stable, but I'm not going to let go of it entirely, right? I'm not going to share it with you. What I'm going to do is I'm going to sign a treaty with you, sign a petition with you that this is just for momentary stability, not a complete bond. I'll just make a momentary donation to you so as to keep yourself stable. But it is not going to be a permanent bond between us. No, I am not up for it. I'll not keep any permanent bond. It will be just a temporary understanding or a temporary donation from me, which is why I have used the symbol an arrow. And this arrow shows coordinate bonds. Any kind of permanent bond or covalent bond, just you can see that I have used single lines, right? But for coordinate bond, I have used an arrow, which means that this is not a permanent bond, alright? It is just a mutual understanding between the two centers. Now, this entire thing constitutes this part, the H3O plus entity, right? So, this kind of situation where there is no permanent bond formation and just a mutual understanding between two centers of keeping each other stable, or the one which is electron deficient stable, is referred to as coordinate bond, which is referred or which is depicted by this kind of an arrow symbol. And compounds which will have bonds like this, which are shown by simple arrows or which are not so-called permanent bonds, are actually referred to as coordinate compounds or coordination compounds, and that's where our topic starts, right? So coordination chemistry is that branch of chemistry which deals with compounds having coordinate bonds, right? So from the next class or from the next lecture onwards, we would move into the depth of the chapter. We will discuss about the things which are mentioned in our syllabus, and also a few more nitty-gritties of the chapter which needs to be discussed in detail. But for now, we shall end the class here with the introduction part of coordinate bond and how the name of the chapter is justified. I hope you guys have liked the introduction and have understood it, which is very important. If you have any kind of queries or questions in your mind, please do drop it down in the comment section below for me to read and get back to you and hopefully clear your doubts. Alright, till then, stay safe and keep revising the chapters which I do with you. Also, if you have any kind of suggestions as to how I should bring about a new topic in front of you, or if you have any suggestions regarding any such topic which you want me to discuss with you, please let me know in the comment section below, or you can also follow us on our Twitter, Instagram and Facebook handles for any kind of suggestions from your side. I would love to see and hear what comes from your end. Till then, stay safe and let's meet in the next class. Bye-bye.